All right. Next Monday, we are going to have our second exam. So the second exam is from chapter 22 to chapter 7. The format is the same as your first exam. We're going to have this time just write a very one short code, and we're going to have 20 multiple choice questions. And all of this will be submitted just like you did the last time to Folio. I'm going to start to introduce advanced data structures. We're going to look at graph algorithms. We're going to develop models for graphs. And we're going to have data structure. When you create an object, the object representing a graph. And you can insert the data for the graph. So those are the vertices and edges, and you can apply operations on the graph. So this is very interesting. It's a subject you're going to study a lot more when you get into the algorithm class. But here we're going to focus on the data structure part. Before we get into the chapters on graphs, we're going to have two chapters. One is on the general graph, unweighted graph, and the second chapter is on the weighted. So these are the chapters 28 and 29. So before we get into graphs, let's look at the program exercise from chapter 27. So this is the first programming project in chapter 27. It's to implement my map using open addressing with linear probing. So here's the template you're going to use here. And we use this template. So I'm going to open this template here now. All right, so this is the template. So look at this is the test code. So here's the main. And so this is the copy from the book, the interface, my map. So here is my hash map. You can write the code to implement it. I provide a majority of the code already for you. And so you need to look at it and to study it. So here, how we do this here, all right? What you need to do is to implement. So here are the methods and the get and put. I'm going to help you on this. Let's do a get. Interesting. All right, so here we go. So this is the, yeah, so this should be okay now. Get, so right here, and get and put. So this is, you're going to write your code here. So let's see how we write for this put. Forget, I'm sorry. So this is the put. Put, you have a key and value. So here, get. So let's see which one I'm going to do it for you. All right, I'm going to do the difficult one. Let's do the put. So the put. Let's open something here. I'm going to, maybe let's go back here. I'm going to use this as workspace here. So here's going to be my workspace. So I'm going to copy and paste this right here. You're going to write the entire code anyway. So here, I'm going to just have this part of it here. So this is the part of it, okay? So how do you write this put? But so this is add an entry. Here's the key value into the map. So this time, so please note that we're using linear probing. So you can use the reference from the book. In the book, we implement it using separate chaining. So now we use linear probing. So please review this linear probing here. Linear probing is that, so you're going to put this entry directly to the hash table. And so you're going to find the index where you're going to put it. Okay. So I'm going to write the code here is first. So we're going to see if this key is already in the map. If this key is already in the map, we're going to replace the old value for the key using the new value. So we're going to write code like this. So here, how do you know if the key is there? So you can use the get key. So we already have this get key for you. So it's a get key. Suppose we have this get key here. It's already here. So we're going to have this is if the get key is not null. Okay. So if this is not null, and so we know the key is already in the map. So, and now it's already in the map. We're going to replace. We're going to have to. The key is not null, so the key is already in the map. So the key is already in the map. So we're going to do a replace. Okay. So how do we do this replace? So we're going to replace the old value for the key using the new value. So here's the new value. This is the new value here. All right. So first, we need to find out the index. So what is the index? So let's say this index is I. All right. I just call this index in the table. So the index is, you're going to have this hash function. So here is the hash function. So where's the hash function? So here is the hash function we're going to use. The hash function. Okay. All right, so we're going to use this hash function. All right, we're going to use this hash function. Okay. So this is the hash. And here is the key. So we'll get the hash code of the key. Okay. We'll get this index. All right. So we have now, let me show you this separate chaining. So look at the visual diagram here for the separate chaining here. All right, so look at this diagram here, separate chaining. We find index here. So we need to compare and see if this is key matches here. If not, we go to next. Okay, until we find one. So, and let's go there. And here is the index. And so we're going to use the while loop. Why this table brackets I. So this is the table here. We have the look, we already have this table here. This is the table we defined here. This is the table. And see, the table is the one, the hash table. So look, this is the hash table. And this is the hash table right here, the table, right? So the table, all right, so the table brackets I. All right, if this is not null, okay. All right, if it's not null, we're gonna compare it. We're gonna compare this if, okay. All right. So just a second, I need to move this. Can you hear me now? Hello?
Yes.
Okay, good, thanks. All right, so we're gonna look at this table now. Table brackets I is not null. All right, so now we're gonna look at this key. Get the key table brackets I. This is an entry now. Unlike in the separate chaining, you have a linked list, but this one is an entry here. So we're gonna compare this key. So let me use I here. This is just shorten this line here. So I'm just using I. This is I. This index I here. And the key is not equal to null. If it's not equal to null, and so if it's not equal to null, and this table brackets I dot key so dot key dot equals this key. All right. All right, so if that's the case, and we have a match here. All right, so we have a match, we can break it now. Break this while loop. Otherwise, we need to continue to do a linear proving to the next one. So the next one is I plus 1 and remainder and this capacity. Okay. All right, so here we have this, we break it. So we find this entry, it's right here. This is the I is the one. So now we're gonna get this entry, we get this, let's get this entry out. Entry, key and value, and this is the entry. We're gonna have this entry now. And this one is table brackets I, the entry. So the old value eventually, so we have to return this old value. So we're gonna have this is the old value will be returned. So we need to get this, we need to return this old value. So here we're gonna keep this old value here. The old value, the type is V, old value is entry dot get value. So get this value. All right, so now we're going to replace the old value with new value. So here, let's do this. Replace old value with new value. And this is the entry dot value with this new value. So that's the one here, the parameter here you passed here. This is the value. And this, and now return the old value here, the old value. All right, so this is only for the case here, if right here, if the key is already in the hash map. All right, else, all right, we don't need to have else because you have, if this is the case, if the key is already in the map, so we always end with a return. So, and now we don't have to do this else, we can just directly write a statement here. So what we do is, we are going to insert a new entry. So we're going to insert a new entry. We're going to insert a new entry. So the first thing we need to do is we're going to check if there's enough space that does not violate the load factor threshold. So we're going to check the load factor, and we're going to look at if the size, the current size, is greater than or equal to the capacity, the current capacity times, and load factor threshold. Okay. So if that's the case, and we need to look at this capacity here, if capacity is equal to now the maximum capacity. Okay. So then we just threw some exception here. Let's just throw exception object new runtime exception. So give a message is exceeding maximum capacity. Okay. All right. All right. So now, if it does not exceed maximum capacity, so we can do this is rehash. Just call this rehash, and to increase the size and rehash everything. All right, so now we're going to insert one here. So we insert, we get the let's get the index. Let's call it I. It's this the hash. It's the key dot hash code. So hash code. All right, so now same thing here. As before, we're going to use while loop here. While look at this table brackets I. If it's not equal to null, and table brackets I dot key is not equal to null. All right, table brackets I is not equal to null, and table brackets I dot key is not equal to null. All right, so it means this cell is already occupied. So we need to move on to the next one. So we're going to search for the next one. So this is going to the next. Okay, keep doing this until you find one is available now. All right, so there's one is available, and now we can put it. So we can put this. And so here we're gonna put this. It's a key value this entry into, so this is going to be table brackets I. And here table brackets I is equal to new my map dot entry, and here's a kv, so here is key value. So this is the one you're gonna to insert it. So after insert it, and the size is incremented by 1, so you need to return and the value. So in this case, you're going to just return this value here. So insert it. So this is the value is to be returned. All right. So this is for this put. All right. So with all this information, and you should be able to do this. I look at how to write the code for get. Okay. So next, all right, I'm going to talk about next class. So just do it one at a time. So please work on this. This is going to take some time to get it right. All right, now we are going to introduce advanced data structure on graphs. So this is chapter 28. So let's look at graphs. You already have data structure, discrete math class. In the discrete math class, and you learned this simple mathematical structure is called a graph. Its graph is very simple mathematical structure. So it just consists of vertices and edges. It has a lot of applications. You can do a lot of things with graphs. It's a lot of practical problems can be modeled and using this mathematical structure graph, and you can solve it. So for example, this map, it's a graph. You have the vertices. So these are the cities, Seattle, San Francisco, Los Angeles, Chicago, Denver, Kansas City. So all this, all right? And now connecting the cities, so we have edges. So this is one edge from Seattle to Chicago, and also from Chicago to Seattle. There's no direction. So this is the undirected edge. Can go both ways. You can think about it. It may be like it's a flat map. So we're gonna think about it. We have just a very simple version of flat map. We have a flight between Chicago and Seattle and Chicago, and between Dallas, Atlanta, and Atlanta, Dallas. So this, you look at this, can be just a flat map. And you can ask this question, what is the minimum number of flights, okay, from Seattle to Miami? So from Seattle to Miami here, there's no direct flight, and you have to go through Atlanta, New York, Chicago, Seattle, or some other route. So what is the minimum number of flights? So that's a graph algorithm problem, and this can be solved. We can write a code and for this, solving this problem. All right, there are many problems. The real life problems can be solved and using this mathematical structure graph. So the graph is a simple mathematical structure consisting of vertices and edges. All right, so now let's look at the basic graph terminologies. So here are the basic graph terminologies. So please look at this very simple easy to understand all these terms. So in mathematics, this is the notation we use. Its graph is G, where this is the equal sign, and here consisting of vertices and edges. So this is in mathematics. So this is how we write it, denote it. Okay. All right. You can represent this, and in programming, you can say here it's a vertices. It's an array of strings, and for the vertices, Seattle, San Francisco, Los Angeles, Denver, Kansas City, all this. See, this is V. It's a set of vertices, and we can represent it using an array, and all using an array list or a linked list. Array list is the most preferred because it's easy to remove and insert vertices and into this V. All right, the edges, you can write the edges like this is in the two-dimensional array, and with this E consisting of all these pairs of these two cities, Seattle, San Francisco, Seattle, Chicago, and Seattle, Denver, and then San Francisco, Denver, all this. All right, so there's a graph. We can define this directed graph or undirected graph as this is the edge. You can see this is the edge. If there's direction on the edge, so from one vertex to the other, so that's called a directed graph with the arrow sign here. So here's a Peter to Mark. So here's Lena to Mark. So this is the direction here. So this really meaning is you can think about it. So this is Peter and Lena, the parents of Mark, and here's Cindy and Mark are the parents for Jill. Okay. So this is the directed graph. So this one is a complete graph. So here is the what is a complete graph? If you have this is every two vertices, you have an edge to connect the two. So this is a complete graph. Now this one is a subgraph from here, this graph, from the graph in B. So you remove some edges, and so you get this is a subgraph. And further, this subgraph is a tree. So what is a tree here is it's a graph, and here without cycles. So it's a tree. All right, so here the terms, what's adjacent and what is the incident and what's the degree. So degree of a vertex is a number of edges incident to it. So here and we have the terms, what's the parallel edges. So the parallel edges here, the example here is a parallel edge here. It's there's two vertices. You have multiple edges, so they're becoming parallel edges. So if there's one edge, there's no parallel edges. So this is the parallel edges here. A simple graph is the one that does not have any loops or parallel edges. Okay. All right, a graph is connected. So it's also known as strongly connected if there exists a path between every two vertices in the graph. Okay. A graph is weakly connected if it's connected when considered in the graph is undirected if still connected. All right, so this is the weakly connected. All right, the cycle is you have a cycle from one vertex, you can travel back to itself. So this travels back. That's the, it's a connected graph, it's a cycle. A connected graph is for every two vertex, there's a path. So they're connected. A spanning tree of a graph is a connected subgraph of G, and that consisting, all the vertices of the graph, and the subgraph is a tree. So that's a spanning tree. All right, so this is terms, and you also can look at this animation. So we have the graph, and so we're going to add vertex, and you can draw a line to connecting the vertex, and here you connect this, and so you can connect this right here, and so you can here, and so add another one here, so this, and you can find the depth first search and breadth first search. We're going to talk about this later in the chapter, and find a shortest path. So how are you going to find the shortest path from one vertex? So for example, from 2 and to 4. So what is the shortest path? So the shortest path, the shortest path here, you can see it from 2 to 0, and then from 0 to 4. So the shortest path here. And it's not unique. You can have from 2 to 1 and to 4 as well. All right, there's a Hamiltonian path, and here's finding kinetic components. So if you have, and here, something here, and this. So what are the connected components? So the connected components in this 3. So all these vertices are connected. There's one component, and here 7, 10 are connected. It's another component, and it's 8, 9 connected. This is another component. So there's connected components. All right, so these are the basic terminologies, and now let's look at this. Representing graphs. All right, we're going to represent graphs. So simple ways to represent graphs. We can use an array, and for all the vertices, it can be string or any object. So here in this case, so we have string for the map. So those are the city names. All right, and it can be any objects. For example, we can make the cities as objects. So here's the city. So city coming from this class, and so the name of the city, population, and the mayor of the city. So this is the city. So you can have, and this is the this is vertices here. It's consisting of city 0, city 1, and city 11. So city 0 and it's object, new city, and city 11 here is object of city here. All right. So this is just a simple illustration. You can use array, but the more flexible data structure and to representing vertices is the array list. That's more flexible. So that's what we're going to use and in this chapter, in the code. Representing edges. So how are you going to represent edges? There are many ways to represent edges. So this is the simple way here, is you can have this two-dimensional array. So we have this edges. So here, 0, 1. So what I'm going to do is this. Look at all these edges here. And this, we assign the index. So Seattle is 0, and San Francisco is 1, and Los Angeles is 2. So this index. So we use this index right here is 0, 1, and that's for Seattle to San Francisco. But this goes both ways. So we have also 1, 0. So this 0, 1 and 1, 0. So this text scale both ways. So this is the is age array. It's very straightforward. So you can put all those things here. This is very good for the input. So if you know the graph in advance, and you can set up your graph like this. But it's not flexible internally. So what happens when you delete a vertex or you add a new vertex? Also, then how you're going to add all these edges? So we're going to use other ways to represent the graph internally. So this is the one. It's very good if you can use it to set up your graph. All right, we can use edge objects to represent one edge. So this is the edge object, is a class here edge, and with two vertices and U and W. So here's the edge. So here's U, W. So here is, you create this edge with this two vertices from this direction, U to B. All right, and here, so we have the equals here, just to make sure, and we have this, if this, you have identical U and V, and so this edge like this, so they are considered as equals. So with this, you can use this edge array. Here is a array list of all the edges. So you can add all the edges to the array list. So this is more convenient. It's internally. It's very flexible. You can add new edges, just add a new object and remove the edge and remove the object from the array list. Array list is easily, it's automatically expanded if you have more edges. All right, there's another representation we have is in the literature, and people use this adjacency matrix. So adjacency matrix is this. It's, you have this the matrix, and you have all this vertices. So this is all the vertices, and here, so there's index. It's Seattle is 0, and we already know it. San Francisco. So here, look at Seattle here. So Seattle is 0, San Francisco 1. So this is all this. Okay. So it's layout like this. Okay. So this, the first here, it's 0 is Seattle to Seattle itself. So it's 0. There's no edge. So here's means this is 1 means there's an edge from Seattle to San Francisco. All right, so look, this is symmetric matrix here. It goes both ways because it's undirected. So you have Seattle to San Francisco, and then you have San Francisco to Seattle. So this is called adjacency matrix. Okay. So this is the, sometimes this can be efficient, and when you represent a very dense graph. So all right, so here's the example. And so for this adjacency matrix, for the graph we have in this in figure 28.3a in the book. So there's 5 vertices. All right, let's look at this representing edges using adjacency lists. So it's this. It's you have all this adjacent vertices. You're going to put them all together in a list. So here's what we have here for Seattle. For Seattle, you're going to have all this adjacency list. So the vertices adjacent to Seattle are in this list. So this is Seattle is 0, and 1 is San Francisco, and 3 is Denver, and 5 is Chicago. So this is, you have 1, 3, 5. Look, 1, 3, 5. All right, so here for Kansas City, so this is 2, 3, 5, 7, 8, 10. So all these are vertices in this adjacency list. All right, we're going to represent it, and further making it more flexible is to put adjacency list, and it's just not just the vertex. We're gonna just also put the edge object. So here's neighbors bracket 0 has this 1, 3, 5. So they are all here coming from this 0, 1, 0, 3, 0, 5. So this is the one we're going to use in the book. It's very flexible. It has a lot of contents. It is also good for you put additional information into edge. So that's what we're going to do in the next chapter. You're going to see we're going to extend it. And so this is how we're going to design it. We can design it using this. Representing edges internally. So we use this linked list of edge objects for the adjacent, all this adjacent the vertices. All right. So with all this, we're going to now ready to design our data structure for the graph. All right. I'm going to do it next time. So we're going to get into modeling graphs. We're going to have a data structure for this graph. So, and let's just give you a heads up. And so what we have is we're going to design this overall architecture. This is going to be weighted graph. Unweighted graph, it's going to be a subtype of unweighted graph. Unweighted graph, it's a subtype of graph interface. So the graph interface, we're going to have all these common operations for graphs in this graph interface. And then we're going to specialize it into this unweighted graphs, and then further to weighted graphs. So this is we're going to have implemented this concrete unweighted graph. So we're going to look at how we do this and next time in the class. All right, any questions? Any questions?
No, sir.
Okay. All right. So if you have questions, please stay and feel free to leave now. Bye.
Have a good one.
See you.